the screen, it looks like a curve. And it will, like if you keep zooming in and zooming in and zooming in your picture, it has to recalculate more points every single time.
So it's just an infinite amount of dots?
Not infinite.
No.
The calculator is actually giving you a finite number of dots that are represented, okay? And making it look like a curve, smoothing it out to make it look like a curve for you. That's what your calculator is doing. So it's not actually, it can't look at this and find X-intercepts because all it's doing is just like throwing up a bunch of numbers. It's like a t-table, right? It just makes a t-table for this right here, makes a t-table and plugs in thousands of numbers, which it can do quick, right? A computer can do a number to the 5th power minus the number minus 1, you know, in milliseconds, right? And it can do a bunch of them. It gives you this plot. So we still haven't answered how the calculator is getting 1.16. Would you like to see the algorithm? Of course. It's Newton's method. Newton came up with this. It's beautiful. And it's pretty much the standard we still use in computers today to solve equations. It's very simple to see how he does it. Go ahead.
Making the intervals infinitely small? Or like
Kind of, yes. That's actually the method that we used before Newton's method, which is your calculator basically goes in there and it plugs in like this calculator. If it plugged in 1, it'd probably get a negative number. And then when it came over here to 2 and plotted, it would get a positive number. And it would say, hey, wait a minute, it changed signs. So it would say it'd have to be 0 in there. So it cuts that in half and tries it again. And then it would say, hey, look, it changes here, here. So it cuts it in half again and tries, and then just keeps on cutting in half, 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 until it narrows it down to this little tiny window. Is that kind of what you were saying? That's actually called the bisection method. It works, but the problem with the bisection method is too slow. Because you cut in half each time. And you've cut in half, half, half. It takes you a long time to get down to like a precision this good. All right? No, let me show you. Yes. Why did I put what?
How did you put it in the calculator?
Oh, that depends on what calculator you're using. Yeah, I don't know. I'd have to go show you. I can show you after class.
Okay.
Yeah, because each one's a little different. All right, so you ready? This is the idea. All right, this is the idea. It's actually pretty beautiful if you just look at it for what it is. Okay, let's say I have a function. All right, let's say I have a function, and I want to know this point. That point right there is the x-intercept of the function, isn't it? So we call this function f. This right here is the x-intercept. How is it that we were told to find x-intercepts of functions? Set it equal to 0, right? So to get the x-intercept of a function, we set the function equal to 0. Right? That's what we've been told for a long time. Okay, so Newton said, look, I want to get to this point, which is just an x value on the x-axis of this function. So if he were trying to do this problem right here, Newton would have said, all right, you see the left side of this equation? That's my function f. All right? And what I want to know is where it's 0, which means I want the x-intercepts of this. So he looked at this and said, well, wait a minute. I'm trying to get to this point. Oh, I wonder if this is just a coincidence. If I pick a point out here, let's just make one up, 2. So Newton would come over here and go, what would I get if I plug in 2 here? Would I get 0? No, I wouldn't get 0, would I? But I'd be maybe kind of close. So he said, screw it, who cares? He would plug 2 into the function, and then he realized that that would take him up to that point. He'd be way off, wouldn't he? But Newton, he's the man with the derivative, right? So he said, look, I can use my derivative to find the slope of this tangent line, couldn't I? And if I know the slope of the tangent line, and I know the point that I'm at, then I know the equation of the tangent line, don't I? So he just said, let me draw that line down to the x-axis and figure out what that number is. Okay, so pick some random point, go up, draw your tangent line, and then figure out where the tangent line hits the x-axis. And then repeat the process. Go up again, draw a tangent line.
So you're just keep taking their derivative.
In there, right?
So wait, by that definition, you would actually
You wouldn't get you wouldn't get to this point in quite some time. Is that what you said?
Yeah, you'd be getting closer to it. You have to like repeat yourself.
That's right. That's right. Exactly. So the method you were talking about, where it's bisection, where you just cut the interval in half and you start to narrow in on it, that is very highly computational. There's a very high operation count for that method. Newton's method, I agree, you're going to have to repeat it, but it's going to get you there a lot faster than the bisection method. They actually they have a name for this type of convergence, like how fast it goes to the answer. It's called quadratic convergence. It's the rate at which it converges is quadratic. And that's the big thing in computer science, is you want to know what they call in big science, big O. Sorry, big O. Anyone know, ever heard of that in computer science? Big O? It's your operation count, basically. You want to know the order of operation, not order like how you do things, but how many operations is it going to take to run the algorithm you need to run? Because you need to know what your computer's capable of. You know? So big O is an important thing. Outside of this class, we're not talking about that. So we repeat the process and go down again and go down again. And actually, we're not even guaranteed we're going to get to the exact answer. What we're going to have is an approximate answer. And the approximate answer that your computer gave you is this. All right? That's the approximate answer. It can't give you an exact answer. It's not going to say pi or something. You know, it's not going to give you square root of 2. It's just going to give you some decimal representation of that number. All right? So let's try this. I'm going to erase here. I'm going to see if we can come up with the algorithm. My other class was able to do it. I asked them, do you want to see the algorithm? They're like, yes. How do you come up with it? And so I showed it, and they did okay. So I think you'll do fine. Okay, my goal is to get to that number, right? I'm going to pick some point to start. I'm going to call this first point right here x sub 0. When I run Newton's method the first time, I'm going to go up and then down, and that's going to create the next number, which is I'm going to call x sub 1. Then I'm going to go up and then come back down with the tangent, and that'll be x sub 2. Then up and then down, x sub 3. And so I'm going to have a list of numbers. X sub 1, or x sub 0, x sub 1, x sub 2, 3, 4, and that starts to converge down to the true answer, right? All right, so let's take this, let's plug it in here. When I plug that in there, that creates an ordered pair. That ordered pair has as an x-coordinate x sub 0. That has as a y-coordinate f of x sub 0. Yeah? Okay. What is the slope of the tangent line here? What's the slope of that tangent line? Good. It's the derivative of the function at x sub 0, isn't it? What's the equation of the entire line then? What's the equation of that? If I continue this line down forever, ooh, wow, that's dead. If I continue this line down forever, what's the equation of that line? So what do you need to have the equation of a line? Slope and a point, right? Yeah. Point and a slope, or a slope-intercept. But here we have a point and a slope, right? We have the slope of the line. We have a point on the line. So the equation is y minus y1 equals m times x minus x1. Remember that? So I'm going to write y minus, what's y1? F of x naught equals m, what's my slope? Derivative at x naught, right? Times x minus x naught. That is the equation of this purple line, right? Now, to get this point, I need the x-intercept of this line. How do you find the x-intercept of a line or a function? Set y equal to 0, or set the function equal to 0, right? So if I take this equation now, and I replace the y with 0, it will allow me to solve for x, won't it? So take that equation right there. So to find this, this is the x-intercept. So I replace that with 0. 0 minus f of x naught equals f prime of x naught times x minus x naught. All right. I'm almost there. I'm going to try and solve this for x. So I'm going to divide this first out on both sides. Divide this side by f prime of x naught, this side by f prime of x naught. And I get f negative x f of x naught over f prime of x naught equals x minus x naught. Did y'all see what I did there? Just divide this. It's not there, right? Zero's gone. Who cares? So divide this. It's gone here. And over there we got that, right? One last step. Add x naught to both sides. And when I add x naught, it's going to come over here and be positive, right? And I'm going to write that up here. I'm going to change the order. It's going to be x equals x naught minus f of x naught all over f prime of x naught. Do you see that with that formula, to find the value of x here, right? To find the value of x, what do I need to know? X naught, which is just some arbitrary point I started at, right? So I get to pick this. This is my choice. I picked that. I need to know the function's value at x naught. So that I can do. I can plug that into the function. Then I need to know the value of the derivative at that point. If I know those three things, that gives me this point. And then what do I do to get the next point? Repeat the process over again. But instead of using x sub 0 here, x sub 0 here, and x sub 0 here, I'd use what? X sub 1. And then to get x sub 2, I'd repeat that. I'm sorry, to get x sub 3, I'd repeat that, but put x sub 2 in here. Yes?
Did you get the 0 for y?
If you have an equation, right? This right here is, this is a line. This may as well have been like y minus 4 equals 3 times x plus 2. That's the equation of a line written in point slope form. If I said, hey, where does this hit the x-axis? That would be the same as replacing y with 0. Yeah? So I took this, replaced y with 0 to get the x-intercept, and then solve for x.
So it's really like you have 2 points. I mean, you have the point on the x-intercept and the point.
Yeah, this point here is x, comma, 0. Yes. So if you look at this in stages, you know, there's a bit going on here. We pick some arbitrary point. Boom. Once we got it, we plug it into the function that gives us a point on the curve. Then we take the derivative at that point, and that gives us the slope of the tangent line. From those two pieces of information, we create the equation of the tangent line. Then we try and find the x-intercepts of the tangent line by setting y to 0, and that allows us to solve for this point. Newton was a man, right? All right, so now the general algorithm. They didn't have phones back then. He didn't have time for that. Well, Newton had absorbed all of the known mathematics by the time he was 16.
Didn't he make it or something?
So he started making up his own.
Did he create calculus or what was that?
Yeah, he's the father of calculus.
It's ridiculous. He had all his time.
I mean, he at 16 years old, he had already absorbed it all. I mean, back then there was no calculus, so it was algebra, and he took it, you know, to the next level. That's what geniuses do.
Wasn't that like during the play? Because he like hit him or something? Like they just threw him like in a little like.
He did a lot of a lot of calculus was created in a shed in his backyard. Seriously.
That was a story I heard.
He worked at his uncle's farm or something.
Yeah, he was basically in a little shed. I don't know, none of you were probably here during the time when a lot of the math classes were out in these portable G buildings.
Oh God.
But I used to teach in those, and people would be complaining about how it was hot in there, and it was, you know, these buildings are sucky. And I'm like, look, Newton did calculus in a shed, and he came up with it on his own. I think we can do this, right?
Like, we didn't even have big
He didn't even have AC. Yeah, we're just trying to figure out what he was doing. You know, we're not making it up ourselves here. Okay, let's get this. His general algorithm is this. If you want to know the nth point, okay, so like here's the 0th point, the next one was x sub 1, then x sub 2, then x sub 3. If you want to know the nth one, here's what you have to do. You have to take the one right before it, x sub n minus 1. You have to subtract from that the function evaluated at the n minus 1 point, and then divide that by the derivative at the n minus 1 point. And that is Newton's method right there. And as you do this, we call this a recursive definition. So in order to get the next value, you have to have the one before it. Have any of you ever seen the Fibonacci sequence? Fibonacci sequence of numbers? I'm going to go way off topic here if I go into Fibonacci, but I'll just tell you what I'm trying to illustrate here.
So you said you were going to go over it.
I won't go too deep into the Fibonacci sequence, but this is the first few terms of the Fibonacci sequence. And the way it works is that the first two numbers in this list are 1 and 1. That's it, okay? It's just they start at 1 and 1. The next number is the sum of these two, okay? And then the next number is the sum of the previous two. So 3 is 2 and 1. 5 is 3 plus 2. 8 is 5 plus 3. 13 is 8 plus 5. 25 is 13 plus 8. And this is a very famous sequence called the Fibonacci sequence. In order to know the next number, you have to know the 2 before it, right? This sequence of numbers that we're creating here, this Newton's method, it creates a list of numbers. But in order to get the next one, you had to know the one before it. That's what this is saying. In order to know the nth one, you have to know the n minus 1. So if you want to know the fourth number in the sequence, you have to use the third number here and the third number here. Understand? And that will start to march its way towards the answer. All right. I'm ready. Let's get this answer. We're going to use Newton's method to get that answer. Y'all look thrilled. All right, so here we go. What I'm going to do is first make a guess. Okay, I'm going to come up with the guess here for x sub 0. So when I'm looking at this and I'm trying to solve this equation, I plugged in 2, right, earlier, and it wasn't true? What if I plug in 1? That might be a better guess. What do I get if I plug in 1? I get negative 1? That's closer to 0 than I was before, wasn't it?
Yeah.
So let's try this with a 1.
But you also realize like it's between 1 and 2 because you're plugging in 2.
Yeah, because I plugged in 2. And, yeah, so, but I'm just going to plug in 1 and start there. So that's my first number. Now I'm going to apply the Newton's method. For Newton's method, I need two things. I need the original function and I need its derivative. Right? I need those two things. So let's write the derivative of this function down. I have the original function is x to the 5th minus x minus 1, and the derivative of the function is 5x to the 4th minus 1. All right, let's plug 1 into this formula. So if I'm going to try and find the next number in the sequence, I'm going to take the one before it minus f at the one before it over f prime at the one before it. Does that make sense? And if I do this, that should give me the next number in the sequence. So now I write it down. This is 1 minus, what's f of, what am I plugging in here? 1, what's f of 1? Negative 1 over, what's f prime of 1? 4. And if I do that, I get 1 plus a fourth, which is 5/4, which is 1.25. Right? Now I repeat the process.
Lovely.
X sub 2 should be x sub 1 minus f of x sub 1 over f prime of x sub 1.
You check first, right? Like,
Check what?
you check your answer to see if it's 0.
No, actually, what I'm going to do is I'm going to keep doing this and then try and see if there's like a pattern in the answers. Let me do another one. You'll see. You'll see. So this is going to be x sub 1, which is the answer we just got, 1.25 minus, f of x sub 1. I have to plug 1.25 into this. Right? But see, this is why the computer can do this, right? The computer likes this. This is just, not algebra. This is just arithmetic, isn't it? The computer can knock this out pretty quick. So the computer now Do y'all see how this works? The computer makes a guess, and then once it has that guess, it starts running this. It creates a new number, takes that number, runs it again, creates a new number, keeps running that algorithm over and over and over until something. I want us to see it, but I'm going to take 1.25, I'm going to raise it to the 5th power. I'm going to subtract 1.25, and then I'm going to subtract 1. I'm getting up here 0.80175782125, something like that. And then on the bottom, I do 1.25 to the 4th times 5 minus 1. I'm getting 11.207033125. Then I divide these two. And so I have 1.25 minus 0.0715406.5. And now I just subtract. And I get as my answer for x sub 2 1.178459,394. Okay? And now I'd run it again to get my third one. Do y'all understand the algorithm, how it works?
But at what point does the computer say, hey, we're good?
Yeah, let's look at that. So I'm going to list these out now. Here was my first one. It was at 1, then it went to 1.25, then it went to this, right? When does the calculator know I got to the answer? Right? When does it know? So what I did is I wrote some code real quick. I actually programmed this to run the algorithm for me. It's a real simple little for loop with a do operation in here for those computer people. All right. Now, I think I changed the function here. We started at 1, right?
Yeah.
Okay, good. This is perfect. So I have this doing it for us. And what it does is it ran it, and it spit out, well, r equals 1 for me in my code means that the first one is 1. All right? So there's 1. And then the next one we got 1.250. I have it actually writing it out to the first 25 digits of precision. So 1.2500000. The next one, when we ran the algorithm one time, we got what? 1.17845939, and then here I rounded it to 4, but up here it's what? 351, all the way out, right? Now watch what happens. You come down, now it's changed to 1.675, right? Then what about the next one? 1.673. So the first 3 decimals have not changed, right? Then 1.673 again, and the 0, right?
That's repeating after a while.
And then 1.67303978226. Holy crap. Wow.
There you go.
Look at that. That one stopped changing, right? That doesn't mean we're there. That means we're there within a certain tolerance. How close do you want me to go? Would you like me to be within, if you want me to be within 1/100th of the true answer, then I could have stopped at this one. But if you want me to be within 1/1000th, I've got to go further. If you want me to be within 1/100 millionth, I'd have to go further. So the algorithm stops when you get to a point that the difference between these is within some tolerance you're happy with. And that's up to you. How far do you want me to go? Does that make sense? Now look, what if I would have started this routine at 2 instead? What if my guess would have been further out? Let the algorithm run. Is it running? No, it already ran it. Yeah, it already ran it. Did it? Yeah, yeah, because look, our first one's this, next one. Look, it's taking a little longer for us to get there, isn't it? But it appears that somewhere around here, we're within, where we'd be happy. You have to imagine if you're like manufacturing something and you need to build something, there's only a certain tolerance you can go to anyway, right? Within a certain fraction of an inch. Once you're out here, I mean, we're talking about significance level that's beyond what's humanly possible to.
The further your mills, the more the cost.
Yeah, yeah. And if you're building, ball bearings for a car wheel versus ball bearings for an aircraft, the tolerances are different in that, right? But the beauty of it is that, look, I'll stop running the algorithm as soon as you're happy with my precision. But how close can I get? As close as you want me to get. So if I change this right here, right? If I change that to, I don't know what's going to happen here. I haven't messed with this, so yeah. Let me change that to 40. Give me the first 40, and let me go back to 1, so that we converge. Those are your first 40 digits. Then we're good. We're good. Ah, right there. Okay, so look. You see that? We got an issue right here. That's where it changed. So if you're not happy with this being close enough to the real answer, then I guess I'll run it a few more times. But it only took how many ways? I mean, how many tries? 1, 2, 3, 4, 5, 6. Within the 7th number, we're at like an infinitesimally small difference, aren't we? This is a really small difference. Yeah. Now think about the bisection method. If I took a number line and I cut it in half, and then in half, and then in half, how many cuts am I going to need to get down to something that's 0.00000000000001, like this far? A lot of cuts. Because it's not cutting it down, narrowing it down fast enough. So the bisection method on a problem like this may take thousands of iterations as compared to Newton's method, which iterated it, 4 or 5 times, and we were good. Very powerful method, very, very powerful. And this is why you can solve equations like the classic equation cosine x equals x. You can't solve that algebraically. There's no way to do it. But if you move the x to the other side, it becomes cosine x minus x. Right? Equals 0. And now this is your function. So your function is this. The derivative is this. And start plugging away with Newton's method. And you'll get your solution. And that's what your computer does. All right, well, that's it. Oh, wait, I thought that said 38. We can make that it. All right, so today was really more of kind of like a miscellaneous day. I wanted to talk about mean value theorem because I wanted you to see it. I wanted to show you, this is the way computers solve equations. It's not some little person inside that's like a math genius that can solve any equation, right? It's just an algorithm. It took a genius to come up with the algorithm, but that's all it is an algorithm. And that's it. On your test, what do you think? Do you want to see a mean value theorem where I say verify? No, on the test. I'm saying, would you like it to be on the test, or would you like to not see mean value theorem? So how many of you would not like to see mean value theorem on the test? Okay, how many of you would like to see mean value theorem? Seems easy. Man, that's almost dead. That's almost dead split. Okay, how about this? Oh, I'm not going to ask you to do this. This is too tedious. This is why we have computers, so we don't have to do this.
That would be mean. You can't use a calculator.
Yeah. Oh, yeah. You have to use a calculator. Yeah, you have to use a calculator for this part.
We'd be like,
There's something that someone didn't mention, and that's in the formula, you need the derivative, right? How does your calculator take the derivative? of a function?
I don't know.
So in Cal 2, you realize that every function can be rewritten as a power function. So like even the sine function can be rewritten as powers of x. So basically like a polynomial. And then that's what your calculator does. It converts it to its polynomial form and then uses that instead.
So everything is converted into a quantity.
We call those infinite series. Yep. It's actually an infinite polynomial, but again, when you're talking about precision, I can cut it off at any point once I'm within a precision that you're happy with. All right, so are y'all saying no for the mean value? How about bonus for mean value?
Yeah.
Everyone can be happy with that? Okay. Well, I guess I have nothing else. Do you have any questions for me? Yeah, I'll show you that. Anyone else questions? All right, study hard. See you on Tuesday. Test time.